All right, ladies and gentlemen, welcome. Well, I thought we'd take a look at the last four problems I assigned, which is our first go at doing this online. So feel free to email me or contact me through on campus, and we're going to give this Microsoft Teams thing a shot tomorrow. So if you have a hard time, let me know, and I'll get to you, and we'll talk it out. So we've been dealing with this thing called thermodynamics, and the first thing we looked at was entropy, which is a fancy word for disorder. So we're looking for anything that is more disordered or less ordered. So in each of these, for example, number 37, where it says predict the sign of delta S for each of the following changes. Well, remember delta S is disorder. So if we're increasing delta S, then our sign for delta S should be positive. All right, so here we are. We're looking at A. And what we got here is a situation where we've got these two flasks with an equal number of evenly distributed molecules, or a situation where the molecules are all very neatly and coincidentally crammed over on one side. Well, obviously, that's a decrease in disorder. So since the system is going from less organized to more organized, that means that the disorder is decreasing and delta S is negative. And we're looking at the same thing in part B. Here we've got a solid. We know that solids are always way more organized. After it dissolves, it's aqueous. Well, you're not going to be able to contain a whole lot of molecules very neatly when they're dissolved in stuff. So the disorder is going to increase by quite a lot. And so since this reaction proceeds from one solid particle to two aqueous particles, our disorder is increasing, and therefore our delta S is positive. Here's part C, where we've got two gaseous molecules, actually three, excuse me, because two of these molecules are hydrogen, and one of them is oxygen. And then we go to what is clearly a liquid molecule where all of these gaseous molecules are now contained in a liquid. Well, obviously that's going to increase order and decrease disorder. So our sign for delta S is negative. And lastly, here's D. It should be obvious for all you chuckleheads. We've got water as a liquid or water as a gas. Well, come on. If you have all your water liquid in a nice container, a nice beaker, a nice sippy cup, oops, I let it all evaporate. Will you ever get it back? No. You have increased the disorder of the universe, and therefore your delta S is positive. All right, that takes a look at 37. Here's 39. It says for each of the following pairs of substances, which substance has the greater value of delta S? Okay, greater value of delta S, higher disorder. And so for this, we're looking at table A19, otherwise known as Appendix 4, some thermodynamic values. And you found this here. I posted this because I'm a nice guy. So here we've got our two substances that we're looking at. We've got graphite or diamond. All right, well, each of these values, each of these substances is going to have a value for S. You see it right here. So all we need to do is find where carbon in both its graphite and diamond forms is right here. All right, well, according to this table, it says here that graphite has a disorder of 6, where diamond has a disorder of 2. Well, that's a pretty cut and dried situation here. So while graphite has a value of 6 for delta S, just S, and diamond has a value of 2, it means that the diamond is going to be much more ordered than the graphite. You can probably figure that out. That's why diamonds are so friggin' expensive. Here we are, part B. Well, come on. A gas is always going to have a higher value of S. Finally, here's another situation. All right, were you paying attention to the last one? Here is carbon dioxide as a gas, carbon dioxide as a solid. I think you know what the correct answer is. That takes care of that one. Number 41 is asking us to predict the overall sign of delta S. And let's remember that for this type of equation, since it's also asking us to calculate delta S for each of these, that we're going to be using the equation sigma n of our products. You guys remember this one? Got this right on the very last day. Subtracting from that the sum of our reactants. All right, well, I went through, because I'm a nice guy, and I found all the values of S for each of these. So for whatever this stuff is, rhombic sulfur, it's got a value of S of 32. Let's find it so you guys know I'm not lying. Where is it? I should have looked this up before I pressed record, but we'll find it. There's our sulfur. But that is, there we go. So it's got an S of 32, right? Cool. So since we know that value, I'm not going to look at the rest of these because I just proved that I wasn't lying, so you guys know I'm good. That means that these are our products, and so we're going to have 3 times 32, and this is the same with our water, 2 times 189. We're going to subtract from that the sum of our reactants. Here we have mercury. Being at home is messing with my brain. This is something called hydrosulfuric acid and our sulfur dioxide. We're going to take 2 times 206. We're going to add to that 1. I'm being overly protective here. 1 times 248. We get a sum of, if you look up here, you'll see it right here, negative 186. All right, and that's how all of these work. So for all of them, you simply want to look up the value of S in the table. I'll give you one more example here. Here's our sulfur dioxide. Well, you saw it right up here, and it's 248, but there are 2 of them, so be careful. You're going to be multiplying those by 2. So for part B, we have a total value of S of 187. Now, before we go on, let's take these 2 values and see if these values of S line up with our predictions. All right. We're going from 2 gaseous particles, 3. There's 2 of our gaseous hydrosulfuric acid, and we've got 1 gaseous sulfur dioxide. That is 3 molecules. They're both molecules are gases. We're going from 3 molecules to 5, which should be greater disorder, but this guy right here is a solid, and that's always going to be more ordered. And so even though we're going from 3 gas particles to 5, but 3 are solids, that means our delta S is negative. And we calculated it, and that's dead on the money. In part B, we've got 2 molecules of sulfur trioxide, but on the product side, we're going to 3 total molecules, and they're all gases, and that means our disorder is going to increase. Totally works because we got positive 187. In part C, we've got a solid, 3 gas molecules for a total of 4 molecules, but obviously iron 3 oxide is a solid. Here are 2 iron molecules, pure iron, which is less ordered and also a solid, but we're going from 4 molecules to 5. We're going from 1 solid particle over here to 2 solid particles. This should be we're also going from 4 molecules total to 5, and so our delta S should be positive. And if we crank it out using our equation, we get 138, which is very, very positive. That works out. Okay, let's go on. Sorry, that's from last year. We did 53 together. All right, and we got a value of our delta G of negative 817, which totally fits. And we should remember from last year that a negative delta G is what ensures spontaneity. Good, we got that, we're cool. Besides, this is the combustion of methane, and if you've had Mr. O for any unit of time, you know that methane is very spontaneously combustible as long as one person is willing to light it. Don't be that person. Let's take a look at number 55 here. This is the last one that I assigned. And you could have used Hess's law to do this one, but I'm going to use the value from Appendix 4 to calculate the value of the delta G for this guy here, which is our sulfur tetrafluoride. Okay? So we should know going in that the fluorine is an elemental, and that means its delta G is always 0. According to the table, Appendix 4, sulfur hexafluoride has a delta G of negative 1105. See? Right there. So that means that we're trying to find the delta G of the remaining, which in this case is our unknown. So here's how I set this up. We only have one product. Let's zoom in a bit. We only got this one product, this guy. So he's going to go right there. On our reactant side, we know the delta G for the fluorine is 0. And we know that we are trying to find the delta G for the unknown. So here's how I set this up. Here's our delta G of our products. Here is the delta G of our reactants. It's the sum, and we're looking for X. So solving for X, I get negative 731. Don't bother looking in the table for SF4. You won't find it. But some of you, if you're feeling really bored because you're stuck at home, you can look up the table, the value for SF4 on some science website, and either they're wrong and you're right, or you're right and they're wrong. Wait, I think I just said the same thing twice. Anyway, so there you go. There's all 4 of those that we started on Friday, and that puts the end of that one. All right, I'll be back with a video explaining how we're going to do the next thing. All right, so you guys all be cool, and I'll talk to you soon.